My name is Alex Gurvich. I'm a third-year PhD student at Northwestern University and one of the Blue Waters Graduate Fellows from last year. Today, I'm going to be telling you a little bit about my project to use Blue Waters to develop a new GPU-accelerated ODE solver that I want to apply to time-dependent chemistry in the fire simulations. So the fire simulations are a set of galaxy formation simulations that are best known for their star formation and stellar feedback prescriptions. And I spent a lot of time thinking about that, but my project is more focused on, my Blue Waters project is more focused on developing a major new capability for the fire simulations, and that's to include time-dependent chemistry. So the time-dependent chemistry is really important for two reasons. One, during the course of the simulation, it has a dynamical effect by setting the cooling rate. So your chemical abundances of your gas particles will determine how fast it's going to cool, and that might, in turn, determine whether your gas is going to collapse into stars. Secondly, after the fact, when you're trying to analyze the simulations, it really enables you to do a much more complete connection to some of the state-of-the-art observations that are being made of like molecular hydrogen and carbon monoxide, things that I'm interested in related to star formation. So to do this time-dependent chemistry, we use the CHIMES time-dependent chemistry network. It's a network of something like 1,000 chemical reactions linking 157 different chemical species like carbon monoxide, molecular hydrogen, and metal ions. And it's a network of stiff coupled ODEs at its core. And here, when I say stiff, I mean that there's just a lot of different timescales involved owing to all of the different physical processes that are being modeled. And so in general, depending on the sort of solver that you're using, you have to either resolve that shortest timescale or things will kind of blow up. But I'll talk more about that in a few slides. As a result, when we enable it, it can take up to 90% of the work for the simulation. So it's spending something like 10 times as much time integrating the chemistry than it is, forming stars or solving the hydro or whatever. And so it's really a target for speed up because it's limited the sort of systems that we can apply it in, and we haven't been able to run it in large volumes or at high resolution. So what about solving ODEs is making it take so long? I sort of hinted, like I said, is this stiff system. So to solve an ODE, there are sort of two classes of algorithms that you can use, explicit and implicit algorithms. Sort of the main difference between them is that for an explicit algorithm, you just have to evaluate the derivative at the current time. Whereas for an implicit algorithm, you have to estimate the derivative at some future time. And in general, this requires some iterative solver to do that, but you can instead approximate that derivative, like say with a Taylor expansion or something, rearrange things, and that creates what's called a semi-implicit algorithm. It's really just doing a single one of these iteration steps. And the nice thing about a stiff solver is that it's guaranteed to converge at late times to the right answer without having to resolve all of those little wiggles of the stiffness. So it's really good for these sorts of problems. So as like sort of a toy example, I have this animation comparing in blue an explicit method and in red an implicit or semi-implicit method. And the goal is to get the right answer in that little red circle. You can see that for the red semi-implicit method, it jumps right to it in just a single step, whereas for the blue method, you really have to decrease the number of steps, so that's what's going on between each frame. Sorry, that number might be hard to read. By up to like 1,000 steps before it really converges to the right answer. Otherwise, you're just wildly off. And so what I've shown is technically really just for solving a single system, but if you wanted to solve a network of equations, you just formulate it as like a vector. You throw a hat on top of your y and your f, and you turn that df dy into a Jacobian matrix, but then everything else remains the same. And so your problem then is really just a problem in linear algebra. And so that leads us to believe, well, what could you use to speed that up? Well, GPUs. So GPUs are massively parallel, and so you have many threads operating concurrently, which makes them really good for vector problems, and especially in other sorts of applications in linear algebra. So machine learning Startups love GPUs for this reason. They can train their neural networks really fast, and it's also really good, for this sort of problem. However, there are some drawbacks, or at least some precautions that you have to keep in mind when you're developing for GPUs, is that memory bandwidth can become a bottleneck if you're not careful. So it's very slow to move stuff from the CPU to the GPU. And even once you have it on the GPU, if you're not careful about your memory access pattern, you can introduce a bottleneck there as well. So to sort of take advantage of the massively parallel architecture and also avoid the pitfalls of this memory bandwidth, a lot of the times you have to really rethink your algorithm or refactor the code that you've been using to take advantage of GPUs, and that can be a lot of work. And as well, sometimes as you move from device to device, the optimal configuration can change. So there are things to keep in mind. But even still, GPUs aren't going anywhere, and I think for a long time they've sort of been described as like the next big thing. I think at this point they're no longer the next big thing, they're kind of the current big thing. Modern HPC resources, so number 1 and 2 on the top 500, deliver 95% of their peak flops through GPUs. So you're not even, you're using only a small fraction of the computer if your code doesn't use GPUs in some way. But of course, why the people who make these computers love them is that they're much more power efficient as well, and so they're cheaper. So the power bill at the end of the month is not so bad. So GPUs. So with those things in mind, I created WIND. It's a GPU-accelerated ODE solver I wrote from scratch in CUDA. And it has 2 solvers, the 2 that I described before, RK2 and SIE. And I have both GPU and CPU versions of them implemented right now. And so I wanted to find out. It's like, OK, so I just sat down. I wrote all this CUDA code. How does it perform? So to test that, I used a simplified chemical network because I wanted to try and apply it to the problem that I knew I would eventually want to solve. So instead of using a network with 157 different species, instead I'm using 5 here. It's just a simple hydrogen and helium network where the physics involved is just ionization and recombination. And so the form of these rate equations is really simple. It's really easy to evaluate. It's just some constant times your different y values. And so I've highlighted those in green and red just to sort of guide your eye into what's going on. So for my test, what I'm going to do is I'm going to assume for each system that the temperature and density are fixed. And the idea is to take some state that's out of equilibrium and run it forward through time to get to equilibrium and see how long that takes. So that's what that looks like here. Starting on the left, we start with both hydrogen and helium completely ionized, and we sort of run it for about a recombination time and see indeed it's reaching this equilibrium level, which I've annotated with those gray lines on the right. So the name of the game is to measure the actual real time it takes for the code to get from the initial state on the left to the final state on the right. But more than that, the system I intend to run it on is not 5. It's not just a single system with 5 equations in it. So to emulate the conditions that we expect to be running WIND in, I repeated these 5 equations until I had a system of 150 equations, and so where every 5 are identical. Now, for WIND, it can't tell that they're identical, and it'll solve them independently. But the sort of operations that I'll be performing will be operating on the same scale. As well, you can take one of these sort of tiled systems and copy that some number of times, again, trying to emulate the conditions that we expect to be running it in when we attach it to the simulation. So here's a sort of scaling plot showing some of those results. So on the y-axis is that wall time to solution, and on the x-axis is increasing the number of repeated systems of size 150 equations. And so the things that I see when I take a look at this are, one, the GPU implementation of SIE in red is outperforming the single-threaded SIE CPU version. So that's good. However, the sort of curious thing is that even though the system was supposedly stiff, the RK2 method is working a lot better. And eventually, the CPU and GPU methods reach parity, but the CPU method is a lot faster. So that's interesting. It sort of led me to believe, it's like, okay, I had this expectation about how stiff my problem was. Is my code wrong? So I tried the same thing where I tiled 75 times. The toy problem that I showed before with the wiggles, which I knew was going to be a stiff system, and tried to see, okay, how does SIE compare to RK2 in this scenario? And this, sort of came back and acted as a really good sanity check, and I saw, okay, yeah, SIE on the GPU is really outperforming all three of the other different solvers, and the other system that we were looking at, you can look at it yourself, is really not so stiff. So even though the full network might be stiffer when we scale up to it, the simple hydrogen and helium network is itself much smoother. As well as we're only evolving through equilibrium and keeping the temperature and the density constant, when we attach to the actual simulation, we'll of course be evolving the temperature along with it because we're trying to do cooling. So it's not the perfect test, but it works for now. So okay, that's if we increase the number of systems. I'll also point out that on my slide I had that I wanted to get up to like 10 to the 6 systems, and for our simulations we have 10 to the 7. 10 to the 8 total particles that we'd want to solve it on. But we're currently limited in the number of systems that we can run because we end up running out of global memory for all of the different Jacobian matrices. So the implementation I'm using assumes that your matrix is dense. But we expect these chemical networks to actually be fairly sparse. And so if we take advantage of that sparsity somehow, there's one, it'll run faster, ideally. But two, it'll also reduce the memory footprint. We'll be able to fit more particles onto the GPU because if you just multiply out 150 by 150 by 10 to the 4 floats, you end up with just a few. Thank you. You end up with almost entirely filling up your GPU's global memory. So I also ran another scaling test. So WIND is a general ODE solver, the way I've written the interface. So you could apply it to ostensibly, whatever system you'd like. And, for instance, we might want to scale up the chemistry or just apply it in a different context altogether. So now instead of holding the number of equations per system fixed, we hold the number of systems fixed and increase the number of equations. So we're increasing the rank of our Jacobian matrix, and we're just tiling this vector more times. And so I want to draw your attention here to this cubed scaling here, and that's owing to the matrix inversion step of SIE, where I've done just a simple Gauss-Jordan elimination. So again, this is the most computationally expensive part of the integration, and it's definitely the target for further optimization. So this is applied to the test chemistry system. We sort of see the same thing, is that SIE, the GPU speedup is okay, but the explicit method is still faster, but if you run it on that toy problem, we see, when the problem is actually stiff, you start to see that benefit with SIE. So the takeaways, as the ecosystem for HPC resources evolves, or really has already evolved, to the point where GPUs are everywhere, you have to start adapting and taking advantage of that, otherwise you're just leaving flops on the table. And so that's what I've started doing now, making this ODE solver WIND, which is a multi-method GPU-accelerated GPU solver, right? ODE solver, sorry. And that we sort of sanity checked ourselves here and showed that explicit methods are more efficient at solving smooth systems, and implicit methods are more efficient at solving stiff systems, where we expect the full package of chimes to be. So the next steps are, like I pointed out, is like taking advantage of that matrix sparsity. We'll get a speed up, hopefully, and we'll also be reducing the memory footprint, like also very importantly. We want to test on more recent GPUs, so all these tests have been run on Blue Waters. But I recently, my PI just recently bought a Volta card, and it just came in the mail, so we're going to assemble it in like 2 weeks, and I'm very excited to try it out. And then, of course, we want to encode the full chimes network and attach it to the fire simulations and actually run some cool science. So I want to take the opportunity to thank the Blue Waters Fellowship, one, for paying my grocery bill, but also for the incredible help that I've gotten from my point of contact as I've been developing this.